Okay, thank you, Catherine. I'd like to welcome everybody in this second training seminar from the series of seminars that are organized by EU-IoT project and also the most recent Internet of Things project of the European Commission. Our previous seminar was on Edge AI and Edge Machine Learning. Today we have an exciting topic on the tactile internet, and we have excellent speakers, some of the best experts in Europe on the topic to talk about the tactile internet, how it relates to Internet of Things, and how it can help us break the time and space boundaries in applications. So I'll just take 2 minutes to introduce the topic. Let me reshare my screen, and I do apologize for this. So what is the tactile internet? Just a short introduction. So a quick and dirty definition is if we can control an application through the internet within a very short time interval, which cannot be perceived by humans. And this is why we say we can break the time, and if this is done from remote, the space boundaries. So typically this is considered less than a millisecond. Now, if you do this, you unblock the innovation potential for interaction, not just automation in a wide range of applications, telemedicine, telesurgery, remote maintenance, which is trending in Industry 4.0 nowadays. Nobody likes to travel, 13 hours from Germany to Mexico, and then another 5 hours in the middle of nowhere in a plant, and many more. And of course, key technology enablers for this is 5G technology, because this provides the ultra low latency that is needed to achieve this requirement of 1 millisecond. Of course, a lot of ultra reliable edge cloud infrastructures and technologies, and the Internet of Things when the things and when devices are involved. So what we would like to answer in today's webinar, and as I said, we have excellent speakers, some of the best experts in Europe for this, is what is the tactile internet? What are the main components of an application? What are some examples of tactile devices? How you enable remote control? What is the role of 5G and 6G in enabling augmented reality applications, but also mixed reality and extended reality? And what's the role of extended reality streaming in various industrial applications? And then you will see examples of applications in vertical industries, construction, precision agriculture, manufacturing, and so on. So that's our program. Without any further ado, I would like to give the floor to Luis Bollinger from Hololight, and he's gonna introduce augmented reality applications powered by XR streaming. So I will, just keep a little bit of the time. We'll have some buffer time, so I'll ask our speakers to take the time and make their points. And we have buffer time for questions and answers. Maybe we can take one question at the end of each presentation before the buffer time. So feel free to ask, to write something on the chat, one question from speaker, otherwise you will have to wait till the end. Thank you very much. Thanks to all of you for joining, and thanks to our excellent speakers. And Luis, the floor is yours.
Yeah, thank you very much, John. Just give me a second to share my screen. Should work now. Yeah, hello from my side. So my name is Luis Bollinger, and I am co-founder and the Chief Marketing Officer at Hololight. And I will talk about enterprise applications that are powered or empowered by XR streaming. And as Hololight, we are a partner also of the Horizon 2020 project in NGIoT. So first of all, in the talk, I would like to focus on the topic XR streaming in general before I will share some examples from some real-world cases. And then finally, I'd like to explain the use cases that we are tackling within the NGIoT project. So let me quickly start by giving an introduction about who Hololight actually is. So we founded the company in 2015, and we are located in Ismaning, very close to Munich, here in Germany. And in Innsbruck, Austria, we have now a team of around 50 people. And since 2015, we work together with a lot of enterprise customers developing augmented reality and virtual reality applications and technology. And one of the major questions and topics that we were seeing in the market and discussing with different customers was basically the question of how to visualize high quality data on mobile AR/VR devices. When we started in 2015, obviously we started with lots of projects because everybody wanted to understand the technology better, wanted to do some POCs, obviously check the business side, but also the technological hurdles that are given. We basically had to handle a lot of digital data. We can also observe a little bit the community and see that more and more 3D content and digital content is produced. And one of the major questions of the future is how are we going to display and work with this digital data? And we believe at Hololight that AR and VR are really key drivers for digital transformation and will be the future solutions of how to visualize 3D data. And if you look on the different kinds of data, for example, data from the building information modeling sector, so huge buildings, including all details, but also 3D CAD data, from cars to machines, point clouds, so 3D scans of environments. But even also if we jump a little bit into the B2C area, realistic game assets. I think everybody is used to have a high quality of data, and a lot of rendering performance is necessary to visualize this data already today on a laptop. But if we then look on the smart glasses side or on the mobile side, then it's really a question of how to visualize these complex and huge amounts of data on a mobile device that is really limited in performance. And this is really a huge issue that we saw in the market because it cannot be a solution to reduce data and lose quality. So the main challenges that we're seeing are really the low performance of mobile XR devices. If you also think about the form factor, in the future, we want to go into a direction where we really have these lightweight devices. There is no space for actually a huge graphic cards or a CPU. So it's limited in performance, and it will stay limited in performance. The efforts for data preparation were crazy in the last years. So I remember a training use case we did in 2016, and just to visualize a machine, we had to invest or use a 3D modeler and rework the 3D model for 3-4 days. And this is a lot of time, and it costs a lot of money. And actually, on the customer side, nobody wants to invest money in just reducing a file or a 3D model.
About the money, I got a lot of money.
Yeah, then the next thing is about the support of different XR devices. Because if you think about having an application that is streamed to different devices, it's really a challenge today for developers to say, hey, I work on a software and I want to support different devices. And the market is really fragmented when it comes to AR/VR devices. So it's a challenge to support different devices. And last point, data security is a huge topic. And yeah, if you want to visualize 3D content on an XR device, it's definitely necessary to have this content being secure, especially in the enterprise sector, but also on the user side, if it's about personal data, this data has to be secured. So storage on the local device, this is a difficult challenge. And we see really the streaming of AR/VR applications as the solution to basically tackle all these challenges. And I'd like to give you a better understanding of what do we mean with streaming. So at Hololight, we have our own streaming technology, which is called ISA, stands for Interactive Streaming of Augmented Reality. And the concept includes basically the three components that you can see here. On the one hand, it's the ISA SDK, so there's the solution itself. Then you have the server side, and you have the XR device side. And usually an application runs on a local device, on a smartphone or on smart glasses. But in this case, the application is no longer installed on the local device. Instead, it's installed on a more powerful server. So as you can see here, the customer XR app is running on the server side, and this can be an on-premise solution or a cloud solution. It can be edge computing, so that's very flexible in first regards. And so what the developer has to do is basically integrate this solution into the app, and then the app can run on an external server. And then we have to look on the connection with the client device, with the XR device. Because on the client, so on the XR device side, we are just receiving a rendered stream. So we no longer use the computing power of the mobile device, but we use the computing power of the external server, which is way more powerful. And then we stream rendered images. So nothing else than a pixel stream, than a video stream. And then the information gets displayed on the XR device, and then the user interacts with gestures or with touch, and basically sends the data back. A new image is rendered, and this is the real-time streaming process that is basically being created. And very important to know is that obviously we are here interacting in a network. The data is sent in a network. So 5G and edge computing are really topics that are also pushing the streaming approach. Because in order to get a real-time streaming, it's necessary to have low latency and a high bandwidth. But we'll come to that later. I'd like to give you a few examples, as I think it's very, very nice to see to get a visual understanding of what's possible with streaming. The first example here is from a partnership Reality, and they basically are having a software which allows engineers from the maritime sector to engineer and work with their ships in some way. One of the main problems is that ships are very old, and not very often all the 3D CAD data is there. So what they're doing is they're making scans of a ship, and they want to visualize it in AR and VR. The problem is that the computing power to render this on the device is not there. But as you can see now here in the video, here we are streaming a point cloud of a ship with more than 1 billion points, which is really, really huge. And additionally, the user here is adding 3D CAD models and putting them inside the ship. So basically, this shows a scenario that is not just limited to the ship industry, but also to all kinds of use cases that have to do with a digital twin scenario. Yeah, without streaming, it would not be possible to visualize such huge amounts of data on mobile devices. I have a second example, and this example is from the automotive industry. Here we are working together with BMW and in Munich, and they basically have long product life cycles for their cars. I think 6-7 years until a car is really ready to go on the market. And this means obviously that they have a lot of engineering to be done in these years. They have a lot of iterations, a lot of hardware that needs to be produced as prototypes, needs to be checked, and they have different tasks which they have to check. And usually the costs for prototypes are very high, and it's very difficult to get them in a short period of time. Even if there is now a 3D print opportunity, it's still not cheap if you create 3D elements that are large in size. And what they are doing basically now is they are visualizing 3D CAD models such as this engine here, put them as a virtual prototype, merge it with some real components, and then they check different things like assembly processes. They check are the things that we are receiving from suppliers, do they match with the work that we prepared? They make design reviews, and they are really able to make concept evaluations up to 12 months earlier. And this use case would also not have been possible if they would not have the chance to stream the data, because such an engine that you could see here has more than, I think, 5, 10, 20 million polygons, so little triangles describing the object. And the limit that we have when using smart glasses such as a HoloLens here, they are at around 1 million polygons. So it's really a factor in between that you can not really cover. With streaming, you basically, in this case, they use an on-premise infrastructure to stream the application from more powerful servers to the device. And this way, they don't need to reduce data. They can use it in high quality and make good design decisions. A third use case that I want to show goes a bit more into the factory planning scenario. It's also like a very common use case in regards of IoT and Industry 4.0. Here we are at BASF in Ludwigshafen, Germany, a very large company in the chemical industry. And they have a whole city of factories basically there. And they obviously need to make changes in the plants, on the machines, but also on the pipe systems. This is a task they basically do on a daily basis. So what they did before is like they planned virtually, and then they went on site, but the situation there was not really the same sometimes. So in order to cover that difference, they are now basically taking their 3D models with them, overlaying them in the real scenario, and have now the chance to basically get a better understanding of their plan. And one of the biggest benefits that they see is in the reduction of downtimes on the plants, because they can make planning decisions much faster. And they are also able to support other plants all over the world in a collaborative multi-user scenario. So yeah, in this case, it's really the same. The data that they usually have, in this case, it's just one pipe system, but sometimes it's way more. It can be like a whole factory full of 3D models. And in order to render huge amounts of data, same thing, it's not possible to run it on a local device. And these are like 3 examples that basically show that with streaming 3D or AR, VR applications, we can overcome the barriers of limited computing power on the hardware side. I'd also like to emphasize that basically extra streaming fits very well to the tactile internet. One thing is, first of all, that on the hardware side, on the infrastructure side, it's actually flexible which infrastructure you use. You can use just a very simple gaming laptop or a workstation, then it would be an on-premise solution, but it can also be an edge computing environment, or it can be the cloud. The benefits are different when it's up to using the server infrastructure side, because when you're using the cloud, many companies nowadays have some security issues, are not yet ready to use such infrastructure. A workstation is very good to go if you just have 1 or 2 users, but if you want to scale a bit and if you want to have an infrastructure on premise, then edge computing is really a way to go. And it's really about having a low latency to stream the data. I also like to say that latency depends a bit on the use case. Because if you're just streaming a 3D model that is floating in the air and you're moving it, for example, from left to right, it's not a big issue if there is like a little delay and the model is going slower than your hand. But if you have an overlay of a 3D model, for example, so you want to overlay this hand and I'm moving the hand and there's like a delay, then it feels very unnatural for the user. And in this cases, it's very, very relevant to have a real-time experience. So I would not say that automatically edge computing and 5G are necessary for all kinds of use cases, but they're empowering a variety of use cases, such as overlaying 3D models. The BMW example that you saw before is exactly such one case. They can use it or sometimes they visualize prototypes that are just floating in the air, but very often they make an overlay of the real object and want to make some changes. And in such a scenario, the lower the latency, the better is the experience for the user. I also like to talk a little bit about bandwidth, as this is also getting more and more important the more we think about rollouts and scalability of AR/VR applications. For example, with our solution, we require a bandwidth of 20 Mbit, and we basically need this on a stable site, as we are always sending the same images. It's not like it's not changing, so it's like always 20 Mbit. But if you think about having really like maybe 1,000 users at the same time going through the network, then latency or the bandwidth is really important. And as we're having more and more multi-user scenarios and people collaborating together, 5G gets very important, especially for these use cases. So to summarize the benefits a bit, with the streaming approach, we basically have unlimited performance, if you want to say so. And this means also that data can be as detailed and as complex as it really is. But it's also about the streaming to different platforms, because if you have your application on a server, it can be streamed to any kind of platform. And so you don't need to develop 10 different applications and put them in 10 different stores. It's about one application streamed to different devices, which is great for the developers creating applications, but also for the companies that want to distribute solutions. And the security aspect, I'd also like to talk about this one here. When you're streaming data, the data is no longer stored on the device itself. So in case the device gets lost or stolen, then the data is basically still protected because it's on the server side, and the companies decide basically, or the company's IT usually say that a specific server infrastructure is secure and is accepted. And if the data is only there, then you're good to go. Centralized management has a bit to do with the platform approach. So if you have one application streamed to different devices, maintenance gets also easier. And I'd like to also talk now a bit about the projects that we have within NGIoT. NGIoT is a project in which we have 3 different use cases, and in 2 of them, Hololight is involved with the streaming technology, but creating also an overall use case. And these use cases are an agriculture use case and a manufacturing use case. And the overlapping concept of these use cases is basically that, first of all, there is a machine that carries out a task and is controlled by an artificial intelligence. So there's no human involved. And it can always be the case that the AI stops the tasks due to some issues. And then there's like a human in the loop that is basically solving the issue and interacting. And yeah, and all these applications or use cases, we also require more performance to visualize the data, and that's why streaming is involved here. So first use case is an agriculture use case. Basically, there is the truck, which is controlled by the AI and doing his tasks. But then let's say there's an issue like a fallen tree, which is blocking the way, and the AI doesn't know what to do. Then in this case, there is a human putting on a VR glasses, having a 360 video screen in front of him. So the cameras that are mounted on the truck. And basically the human is now interacting and moving the car and telling the truck what to do. And this way also the artificial intelligence is learning, and next time might be able to go around the car, around the tree, for example. And here the data that we're visualizing, so this 360-degree video screen plus all kinds of data requires really some performance that we are not having on mobile devices. And use case 3, basically because we're leaving out the healthcare use case, is about robotic arms that are doing some tasks, and an AI is controlling them. They have some customized tasks that they have to do. And in case they don't know, for example, how to grab, for example, an object, then there is like an issue communicated to a human that is basically taking over and telling the robotic arm how to grab this object. And for this use case, the user is basically putting on an AR glasses and seeing a digital twin of the robotic arm, but also seeing a 3D object of, for example, a CNC machine. And this data, same thing, very complex to visualize, and you need to see some details to really perform or to really give some precision to the use case. And here it's the same thing. It's an AR application that is streamed to the user and is basically solving this issue. So very interesting use cases where we can basically add the human factor to an artificial intelligence use case. And all these use cases are basically benefiting from XR streaming. Yeah, I hope I could give you some ideas and some examples of how this really looks like, how it feels to have a streaming use case. I think roundabout in September for the IntelliAIoT use cases, we might have some video material also to demonstrate more what these use cases, how these use cases really look like. So I'm looking forward to this date, and hopefully can share this then in one of the next sessions. Thank you very much.
Thank you very much, Luis. Are there any questions to Luis, since we have 1 minute for questions? What I wanted to ask you, Luis, if you can, of course, disclose this information, but for the industrial customers cases, you showed in the beginning, like BMW, what is the network they are using? Is it a private 5G network or a more conventional network? If you can, again, disclose this information.
Yes. So we're basically starting with a 5 gigahertz Wi-Fi network. And this is already covering some use cases, but for example, the overlay of 3D models gets to a certain limit if you're using this network infrastructure. So at the moment, there are definitely discussions within BMW, within BASF. They all investigate 5G as a potential new network, and they also think about the cloud solutions. Yeah, so it's in progress, and I'm sure that in the next couple of years they definitely go to this networks.
So this means that you can do XR streaming, right, with current networking technology, but the full potential you need the 5G.
Exactly. So we're coming to certain limitations depending on the use case.
Okay, thank you, Luis. I don't see any other question in the chat, so I would like to thank you once again, and then go to Christina to see Nokia's perspective. With emphasis on remote control, on the use of augmented reality for remote control applications. Christina, the floor is yours.
Thank you. 1 second that I put everything. Hello, can you see my presentation and hear me?
We can hear you, and we can see your presentation. So,
thank you so much. So hello, I am Cristina Escribano from Nokia Ben Labs, Spain, in Madrid, and I'm going to talk about augmented reality and virtual reality for remote control over tactile internet. First, I want to thank the organization of this training workshop to allow me to be here, and thank everyone for attending today. I am currently working at Ingenius, that is a European project that has a lot to do with concepts as IoT, 5G, or tactile internet. Ingenius aims to design and evaluate the next generation IT solution with emphasis on 5G, providing smart networking and data management solutions with artificial intelligence. I'm going to talk about a use case of this project that merges virtual reality with robotics and tactile internet. So the Internet of Things, or IoT as we call it also, is a system of interrelated computer devices, mechanical and digital machines, objects, or people embedded with a sensor or software or other technologies for the purpose of connecting and exchanging data over a network without the requiring human-to-human or human-to-network interaction. The IoT aims to unify everything in our world under a common infrastructure, giving us not only the control of the things around us, but also keeping us informed of the state of those things. The Internet of Things is growing and contributing drastically to improve the quality of life. The technological innovations and growth are a key factor in the IoT progress. As Tactile Internet, we understand the internet with the characteristics of low delay for enable the transmission of tactile information. It has attracted attention for being one of the core functions of 5G mobile communication and enable to enlarge the immersive feeling in mixed reality technologies. Here, the word immersive is used to describe experiences that completely surround a person, to make them feel part of the alternative environment. The immersive technology is any technology that extends the reality or creates a new reality by leveraging the 360 space. Because immersive technology provides the 360 space around us, users can look at any direction and see the context. Some type of immersive technology and extended reality are digital images on a user environment. Other can create a new reality by completely shutting a user out from the rest of the world and immersing them in a digital environment, what we call virtual reality. As you all can understand, Tactile Internet has a lot to do with this immersive experience. To merge these two concepts, we must introduce the haptic technology. The haptic technology, also known as 3D touch, and unlike other examples of immersive technology, involves tactile feedback by using pressures, vibrations, and movements. The elements are all used to give the user feedback based on their actions or environment, creating an immersive experience simply through touch. Simple haptics are already widespread in smartphones, using a haptic vibration to silently notify users without the need of ringtones. However, haptics also have useful applications in industry context. The development of haptic gloves can allow users to interact with remote objects or equipment. The main point of all those technologies is that they need a quick information flow. The tolerable delay time for tactile internet has been set as 1 millisecond. So that so the users may not have an unnatural feeling when receiving tactile information through the internet, since the tactile sense is the most sensitive delay time among the 5 human senses. The minimization of the delay time between communication systems to less than a few milliseconds will improve the communication quality felt by the end users. That's why those technologies are understood inside the 5G environment. 5G includes the ultra reliable low latency communication, known as URLLC, as one of the key technical aspects. As my topic is remote control, let's introduce a bit this concept. Remote control for vehicles or teleoperation driving, as defined by the 5G Automotive Association, is critical for the massive deployment of fully or partial automated vehicles scenarios. The teleoperation driving will be managed by remote operators or automated system connected to the same network where the vehicle is located. Human or not human operators will take driving decisions based on the real-time information provided by the multiple IoT sensors. Those sensors are board on the vehicle and also are board on the cockpit used by the human operator. We will talk about that in a few moments. The accuracy of the sensors and the low latency path from the sensors to the operator will be able to provide the maximum precision for the remote operation. The accuracy and precision of the diverse actuators on the cockpit and the vehicle will also be critical. The major difference between a traditional human vehicle operation and a remote driving operation is the additional delay introduced by the telecommunication network in two ways: the delay from the vehicle to the operator with the telemetry information, and the delay from the operator to the vehicle with the command sent to keep control of the vehicle. So, in our use case inside Ingenious, we are focused on a driving teleoperation of an automated guided vehicle, which I would call AGV in the rest of the presentation, with a virtual reality and a haptic solution. This vehicle that we can consider as a four-wheeled mobile robot operates at Valencia port, helping in supply chain processes. AGV, automated guided vehicles, are widely used in industrial scenarios. With IoT and virtual reality and haptic technologies, we can implement a teleoperation in which a pilot can drive this AGV from a remote place. This teleoperation allows safe driving performance in which potential hazardous situation given on an industrial environment can be avoided. To achieve the objectives, we have implemented the structure shown in the slide. A remote human operator with virtual reality glasses, haptic gloves, and a wheel and pedals control the vehicle. The remote driving operation features a 360 immersive cockpit in which the remote pilot visualizes with the virtual reality glasses the video streaming of 4 video cameras that are attached into the AGV and a full set of telemetry indicators that provide real-time information of vehicle sensors. The virtual reality application shown in the glasses is based in a realistic 3D vehicle model that is used to create an appropriate real vehicle environment for the driving. The Ingenious vehicle is an AGV that has no a real wheel or seat for driving. So we needed to create a virtual environment to make a comfortable driving experience for the operator. Textures, colors, or models could be updated depending on the operator preferences. For the teleoperation driving system, the video quality will be critical. The bandwidth for the video is high, and the constraints for the video information are the frame rate, the limited compression for low latency video, and the video resolution. The tactile IoT is provided by the vehicle sensors and actuators, but also by the remote cockpit sensors and actuators. The haptic glove provides sensing of operator hands movements and is able to actuate in the hands skin. The cockpit provides a real wheel and pedals built for gaming with high accuracy. The backend application captures the human-wheel interaction and transforming to a command that can be understood by the vehicle, by the AGV. The AGV that we are using is implemented with ROS, that is a robot operating system. So we had to translate the wheel and pedal movements to ROS velocity commands to allow the control. Furthermore, we have implemented an obstacle avoidance in which the AGV with a depth camera is able to detect obstacles and stop when they are close enough. The communication components of the teleoperation driving system will include a module that format periodically all the sensors or actuators information. This information flows are sent from the vehicle to the cockpit and the cockpit to the vehicle, crossing the backend application. Its information flow may have different latency and bandwidth requirements to guarantee a given field of teleoperation remote control service experience quality. Sorry, I didn't pass that. Well, it's okay. So talking about the connectivity, the internet connectivity is provided by a 5G network that can support diversity of network configurations that guarantee end-to-end latency and bandwidth between the vehicle and the remote cockpit. As we said, that was the key part. The information flows will be mapped into slices that will be dimensioned to support the remote operation requirements. The network will also include a multi-edge computer very near to the vehicle to host the teleoperation driving backend application that will support the authentication and key performance information and monitoring. 5G network slices will include 5G quality of service identifier for radio and quality of experience for transport links and virtualization resources allocation for components required to guarantee the remote control use case requirements. The security implemented by the application and supported in all the components is the following. The vehicle will include a certificate that will be used for a VPN communication channel for the service provision. If the vehicle do not receive the telecontrol constant message, or in case some vehicle sensors or actuators are falling, the vehicle will stop the remote control operation. The cockpit will include a certificate that will be used for a VPN communication channel for the service provision. If the cockpit do not receive a telemetry constant message, or in case of some cockpit sensors or actuators are falling, the service will stop the remote control operation. And finally, the backend will monitor the network KPIs and the service KPIs. In case of some of them are not guaranteed, the service will stop and the teleoperation will stop. Backend component will also support service management features as authentication and resources allocation for remote drivers. As a summary, we have implemented an AGV remote control based on the IoT sensors and actuators, working with a 5G low latency networks that enable the appropriate data transmission to allow a full immersive environment to the operator. Now I'm going to show you how everything works with a video. In it, you will be able to first see the cockpit that is used by the operator. Then you will see the AGV being remotely controlled. And finally, you will see the virtual reality application visualized in the virtual glasses. I mean, what the pilot actually see on the virtual glasses. Be careful because I think it's a little bit loud, but I guess it's okay. And that's all. I hope you enjoyed the presentation. Thank you.
Thank you, Christina. We have a question, which is about the speed of the network that you need for implementing this virtual reality use case.
The speed, I cannot say a
number or
value, but we are, as you could see on the video, we were operating near the 5G antenna that I don't know if you saw it, but it appeared on the video. And we need a really fast internet speed with a good 5G covered, because otherwise it wouldn't work, or it would work but not as expected. So let's say that this is a key part, a key value that we have to achieve. But now I cannot exactly say the number because I don't remember. Sorry.
Okay, thank you, Christina. I don't know if there are any other questions. I just read what I saw in the chat. Otherwise, I'd like to thank you for the presentation, but also for the demo, which was, it helps a lot, understanding how things are in practice and how perfect or imperfect they are sometimes. So thank you very much for the presentation. And I think we can move to Piotr Dimarski, that he's gonna talk to us about the applications in the construction industry. So Piotr, the floor is yours.
Thank you. My name is Piotr Dimarski, and I'm head of the digital transformation department in construction company called Mostostal. I will stop my video, and I will short my presentation.
Yes, we can now see it. Thank you, Piotr.
Perfect. Just quick introduction of my organization. Mostostal is a general construction and in Poland, and we implement projects in all key sectors of the construction market. As a digital transformation department, we are involved in the implementation of European projects related to the digitalization, IoT, and building information modeling, which is the current revolution in the construction sector. Our projects that are listed on this slide concern the following topics: building renovation using BIM tools, create training methodology related to the BIM to increase skills and competence construction workers, BIM tools development for building renovation project, and at least one is a IoT project that I will present during this presentation. So let me start with the concept of a IoT project. This IoT was born to solve the needs that exist today at the time to generate, process, or monitoring the large amount of data and information from IoT ecosystems safely and in real time, which usually come from the smart industry. Also, Assist IoT aims at tackling the challenge that the next generation technologies related to the IoT are posing. Which are these challenges? 5G, artificial intelligence distributed, shared, and everywhere, smooth incorporation of HR, VR, and mixed reality devices and tools, achievements of outstanding low latencies, and communication and interaction with the user. The Assist IoT concept consists of the creation of a multi-layer architecture based on the model of Tactile Internet, which offers low latency and uses edge technology. According to the architecture defined for the project, any functionality to cover next generation IoT needs will be inserted in the form of an enabler, which is an abstraction of technological components that can be added to the main structure of the solutions to incorporate key assists like distributed ledger technology, network functions, virtualization, 5G connectors, HR or VR interfaces. And as an overall, Assist IoT is being created to transfer the intelligence closer to the user and to the data source, moving the computing capacity among that is called the edge to cloud continuum. The main objectives of Assist IoT are to provide scalability and flexibility to solve the needs of the industry and to provide more secure, efficient, and reliable IoT environments and to collect human and environmental data for the development of AI applications. With some clearly defined objectives, Assist IoT is looking for devising an architecture to cover them all, and also is aiming to demonstrating the success in 4 use cases separated in 3 pilots corresponding to 3 different industrial sectors. To achieve these objectives, the steps will be the following: the design, implementation, and validation of NGIoT architecture, the development of pilots in real life, and the development of network and distributed components and tools, the cooperation and entering the market with something new. Assist IoT ambitions are decentralized architecture, have hyperconnectivity and interoperability, have a strong privacy for data, implement an efficient and distributed protection system for data, and develop human-machine interfaces, and the creation of ambitious pilots and scenarios. Now that we already know what Assist IoT is about, let's focus on the main aspects of Tactile Internet. What does it consist of? Providing the human and feeling of touchness mean that reaction with their hands, motions, reactions will have effect in a time that is not perceptible by the human eye or other senses. A system with low latency, high reliability, and high data throughput. Why is it important? Respond to the current needs and demands of industry use cases, scientific community trends, and standardization initiative gaps. Will allow the next generation and functionalities become a reality, expanding beyond our perspective on the technological possibilities. To achieve the feel of touchness, it has been studied that the data handled must be considered as a haptic data, so that the human will not feel any delay. Haptic data is defined as any data created to provide haptic feedback, which allows user to touch, feel, and manipulate physical or virtual objects through remote machines. Here, the data rate is 1 kilohertz or even higher. To achieve the implementation of these features, it is necessary to take into account parameters that are related to humans, such as skin parameters, which involve properties that have to do with touch, temperature or skin, or kinetic parameter that it has to do with the position and mobility of parts of the body. On the other hand, the applications developed with these characteristics can be grouped into two groups. Those that don't tolerate any type of latency with transmitting the information to be reproduced by the receiving machines, and those that have tolerance. And this slide shows that ICT has been designed to tackle the tactile internet issues and demands, which with the aim to cover all necessary aspects. First, following the master-slave paradigm, the users will act upon devices. Second, the different access networks, gateways, and other communication technologies will be in charge of achieving low latency. To cope with that, IoT allows a wide variety of technologies to be incorporated and integrated in deployment. Regarding the network plane, the use of SDN switches and AI technologies to minimize latency and routes will aid tactile internet to effectively take place. About the data management, and diverse enablers for converting data into haptic data will be inserted into the architecture. And finally, one of the principal objectives of the platform are the flexibility to adapt the different situations, being independent in terms of domain, and to be a modular platform. In IoT, we have three different pilot scenarios to test developed solutions. Three pilots representing port automation, cohesive vehicle monitoring and diagnostics, and smart safety of workers. First, let me explain why construction companies in IoT project. And the graphic on the left explains why topic related to the safety is so important for us. It results that in the construction sector occurs 20% of all fatal accidents at work in the EU-27, and non-fatal accidents are also relatively common at the level of 11%. This shows that currently used prevention measures are not enough in order to provide workers healthy and safety. And moreover, accidents at work lead to delays in construction works and even can stop construction in case of fatal one. And to demonstrate smart safety of workers, we selected current construction site located in northwest of Poland in Szczecin. And the construction site consists of renovation and existing building one. Together with other partners in the projects, we defined 4 business scenarios related to smart safety workers pilot. The first one is related to the occupation safety and health monitoring. It responds to the main problems of the construction site, like risky and changeable work environment and lack of tool for real-time monitoring of incidents and life-threatening events. The role of the platform will be providing a better control to the construction site access as enforcement to the danger zone only by unauthorized persons, and interactions between workers and construction sites will be also monitored. Besides that, type of hazardous event and place of its occurrence will be notified in real time, and thanks to this, the rescue operation can be delivered immediately. Our approach within the IoT will have a significant contribution to the current state of the occupational safety and health management. We will move from the periodically conducted to real time, and from collective to personalized risk assessment, we believe will contribute to the reduction of accidents in the construction sector. And the second business scenario is devoted to fall arrest monitoring. In this scenario, first, falls from height are detected. Second, Safe and Healthy Manager is informed about the localization of construction workers suspended by their smart fall arrest equipment. For the need of this scenario, Central Institute for Labor Protection, National Research Institute, working with new ways, will develop a fall arrest detector. The third business scenario is about safe navigation. As it has been already mentioned, construction site is a very changeable work environment where subcontractors change frequently. They may not be aware of all dangerous zones at the construction site. Platform will provide the information about the current dangerous zones using geofacing and geolocalization. And besides, at the time of evacuation, the platform will indicate to the worker the best escape route. And the last business scenario is related to support and safe and healthy manager during the inspection at the construction sites. The system will help in identification of construction worker during safe and healthy instruction or observations. Additionally, Safe and Healthy Manager will easily check the current permits of employees or expire date of the medical test. Distributed ledger technology guarantees secure and unchangeable data that can be used in case of control by the state labor inspector or litigation. On this slide, you can see a summary of the requirements regarding the tactile internet on our pilot. As you can see, the focus is on accurate employee location service and enough communication bandwidth. At the end of my presentation, we can ask a question: is the construction market ready for a revolution? At the end, the answer is that the revolution is already happening. On this slide, you can see the comparison between the actual status of the construction works and building information model. Augmented reality for facility management helps us to identify installation and equipment in the building. And augmented reality is also used to be checked the correctness of the mounted elements. And in this case, the window, as well as it's possible to check the correctness of the design project by applying the beam model of the mechanical, electrical, and plumbing installation to the current state of the building structure. As you can see on these photos, you can detect mistakes before start and the installation works. And this on this slide, you have listed partners of ASIS IoT project. Thank you.
Thank you, Piotr. I don't know if there are any questions. What I'm really curious, because this construction setting, is not an easy setting, right? Also from my experience from other projects. What is the setting where you validate this case? Is it a lab, or it is a real construction site? I mean, outdoors,
Yeah, so first of all, we will test it in the lab of the Central Labor Protection Institute. Also, we have partner Orange Lab Poland that is responsible for the all things related to the communications. We are planning to make small tests on our construction site, but we also planning to test whole platform in a real construction site to check communication. Till now, Mostostal as a construction company, in a previous project, we have we tested technologies, communication protocols like Zigbee or ultra wideband, and now it will be the first time when we will try to test communication 5G in at the construction site, which, as I said, it is very changeable environment. We still don't have the final hardware solutions. In our projects, we will have open call for external developers at the end of this year. So some solutions will be developed also by the external partners. The project started at November the last year, so we are on the first phase of the project.
Okay, interesting. Also, there's a question from the audience. Tommy Scarpling. I don't know if Tommy would like to open the mic and answer. Basically, the question is, how do you solve the positioning problem in the indoor environment inside the house?
It's very challenging because we want to work on the construction phase. It's very easy when you finish the building and you install some tags where no one will destroy them, and you use it for the building management, using with the building management system. But in our case, it will be the very difficult changeable environment during the construction site. So I suppose that we will have to install some tags on some gateways or doors to follow the users. But sincerely, we still don't have the final list of the equipment. It should be done at the end of this year.
So the idea is that you are going to have some tags, right? And you're going to use classical methods like triangulation and so on. But the problem is what happens if the tag is removed or damaged and so on. I don't know if I get it right.
Yeah.
Okay. I don't know if Tommy, if this answers your question.
Yes, thank you very much.
Okay. Thanks for engaging. And with this, I think that unless there are any more questions from the audience, if not, we can move on to Synelixis, Stavroula Bourou, and she is going to talk about Internet of Things and extended reality, the role of 5G and 6G. And I think Stavroula will also give us a bit of a tutorial concept on the tactile internet and extended reality, which is always very nice to attend. So Stavroula, the floor is yours. And we
hello,
can
everybody.
Your presentation.
Yeah, okay. So hello, everybody. I'm Stavroula Bourou. I'm working in Synelixis Solution, and I'm going to present a presentation about designing IoT-powered XR services and application towards a tactile internet. I hope that you are seeing my presentation and you are hearing me and everything is fine, so I can start. Yes. Let's start from the overview of the presentation. Firstly, a short introduction about extended reality. Sorry, okay, better now. A short introduction about extended reality will be given. Afterwards, we will investigate how AI can enable smart XR services, and particularly the way that machine learning and deep learning models are able to strengthen XR. Then some essential information about IoT-powered XR services and application will be described. At the end, the potential XR open issues toward a tactile internet will be presented. But okay, let's see what is extended reality. So extended reality refers to all real and virtual combined environments and human-machine interaction generated by computer technology and smart devices. In other words, extended reality encapsulates augmented reality, virtual reality, mixed reality, and everything in between. So, as I said before, extended reality can be characterized as an umbrella for augmented reality, mixed reality, and virtual reality. Augmented reality is an experience with limited interaction that superpose digital content and information onto the physical world through cameras. Augmented reality employs mobile devices and various headsets. Mixed reality blends the physical and digital world while the interaction in between grows. Microsoft HoloLens and other headsets can explore mixed reality environments and interact with them. Virtual reality is a simulated experience that can be similar to or completely different from the physical world. There can be little to no interaction with the real world. Smartphones and tablets can provide a limited virtual reality form with PC. Powered devices such as Oculus can provide many features with great virtual representation capabilities. So now some information about the most famous framework, tools, and handsets for building an XR application or service. Unity 3D is a cross-platform game engine developed by Unity Technology. It is really popular for mobile development and used for games such as Pokemon Go, Call of Duty, and etc. and some other. Finally, it's easy to use and fully support XR application development with this platform. Unreal Engine is a cross-platform game engine developed by Epic Games. Initially, it was developed for PC games. Unreal Engine is a complete suite of development tools capable to deliver high-quality visualization and immersive virtual worlds. To develop XR application, the developers must use the corresponding SDKs on top of Unity or Unreal Engine. The most famous for AR applications are Vuforia and AR Code. For virtual reality application, every virtual reality headset, for example, Oculus, comes with its SDK. For mixed reality, the most advanced and popular headset is the Microsoft HoloLens. One of the first limitations is related to ethics. So current limitation and challenges is important things in the XR and generally in this kind of service. So about the ethics, the designer of a XR service or application should prefigure the impact of the experience on people and avoid possible problematic situations. The XR must provide immersiveness, but in a balanced, user-centric way. Of course, XR must adapt to GDPR rules. Regarding the current limitation and challenges in technology, privacy and security is the first one. This is also an ethical and legal issue. Technologically speaking, all it takes is one weak point in the overall system for the integrity of the entire XR system to be compromised. Think of the sheer amount of personal data that an XR application could collect, store, and transmit for my biometric information to our personal details that could easily be taken advantage of by adversarial attackers. XR services and application must be as realistic as possible and require real-time data processing to achieve immersiveness. Thus, there is a need for IoT devices with strong processing capabilities. Moreover, an IoT device should carry small sensor and lightweight devices in order to be more transferable or to limit the physical effort of carrying it. Another challenge is that XR services must adapt to 5G networks and push the data preprocessing to the cloud. Therefore, there will be no reason for on-device processing. A big challenge for the future of XR is the real-time multi-user interaction. To this respect, multi-user safety and awareness come first. In a multi-user scenario, an XR application should focus on collaborative learning, training, creating, and sharing among participants. Regarding the data collection and processing, it's crucial for the extended reality to recognize faster, better, and without haptic controllers user gestures. Also, fast algorithms for real-time processing and mandatory for finer results. So now let's see how the artificial intelligence can enable smart XR services. Let's see a brief overview of AI technologies. AI refers to the field of computer science in which a system performs human-like tasks such as speech and text recognition, object detection, problem solving. AI involves a set of various technologies. Machine learning analyzes huge data, learns from it, and improves itself based on its experience. Deep learning is a subset of ML, able to work with complex, unstructured data such as audio, video, and images. Computer vision is a field of artificial intelligence that trains computers to interpret and understand the visual world. Using digital images and cameras and videos, the different deep learning models, the machine can accurately identify and classify objects and then react to what they see. Natural language processing understands human language context and extracts meanings. When AI techniques is combined with XR services, then a powerful and innovative solution is created, which can successfully manage complicated operations and complete systems. XR technology allows visual experience that merge computer generated items with a real surrounding environment, providing a visual extension of the reality. Thus, the user is able to see things combined with the real environment. Additionally, XR headsets are equipped with microphone and speakers, allowing an exciting audio experience with spatial sound. Sound in XR devices can be heard from all directions, creating a 360-degree world of acoustic holograms. Furthermore, in XR services encounter the Haptic Technology, which is designed to immerse and simulate our sense of touch with various mechanical components. So the user can select computer-generated items, move them in the space, rescale them, or select them generally. It is understandable that AI technology can be a valuable asset to XR solutions. Artificial intelligence powered XR experience could open the door to a new world of innovation, providing immersive experience. Machine learning and AI and XR could become the pillars of the solution, offering awareness, intuition, and immersiveness to the user. At the end, you can see that we can say that XR with AI combined together, they lead to an intelligent system. But what can AI do for XR? Briefly, we can say that AI can analyze the surrounding environment and derive meaningful information. The two main AI technologies that can be used in XR are computer vision and natural language processing. Specifically, the XR headset through cameras can visually understand the real environment, and by AI-based models can perform different operations like object classification or detection, scene understanding, or movement analysis of people near of the user. XR headset through microphones will understand the conversation which is happening by AI-based automated speech-to-text methods. AI models will understand what is being spoken based on the audio, speech-to-text algorithms. Or AI models can perform automatic speech recognition, sentence prediction, and spelling correction. Speaker identification is another task that can be achieved by AI models. And where can XR with AI be combined? Those are some use cases that can be used together in industry, in training, in smart farming, and personal assistance. In smart farming, XR services with AI technology can be used for precision agriculture. Specifically, crop conditions will be observed, and AI pythons will identify ripening stage of crops or even detect diseases. Then the result will be projected to the farmer by XR glasses, giving the opportunity to simultaneously see the crop, but also the related information about them. In industry, XR coupled with AI models can be used to assist workers with equipment and processes for quality control of the production. The AI models could offer faster decision making, and the whole situation, the whole solution will reduce the errors. In personal assistance, the XR can be powerful virtual personalized assistant. The service can be personally profiling and learns preferences over time. To achieve this, contextual intelligence is required. Finally, virtual training can utilize XR and AI technologies to achieve faster learning. Additionally, risk-free and safe experiments can be performed using the XR headsets. With XR and AI, the learners can have customized lessons with adaptive content for a more appealing experience. It's worth to mention that in those use cases, IoT devices can also be used, like camera sensors. Then all the observation will be fused and uniform output will be generated. So let's see now about the role of IoT device in XR services and applications. Initially, we can say that IoT and XR are complementary in a way. To mention some general information, more than 20 billion IoT devices are connected that collect more than 22 zettabytes of data. With the term IoT, we are referring to devices that collect data like smartphones or sensor, cameras, etc. The role of XR technology can be crucial since it can change the way that humans understand data. Particularly with XR, the collected data from IoT devices can be visualized. It's important to notice that the tactile internet through 5G networks will lead to innovative XR glasses. Moreover, due to the fast connection capabilities that 5G network preserve, the processing will be done on the cloud and not on the device. Here we can see some applications where the XR services and IoT can be used. For example, it can be used in healthcare, in industry, in retail, in education, and for emergency response. To sum up, let's see now the essential components and technology that should be considered in order to create a powerful XR service. Of course, with IoT device. One important component is the game engine. which is a framework for creating high quality graphics, mobile apps, and many more things. Then IoT technologies can play an important role, since they can strengthen the XR service and applications. The XR framework should be chosen based on the requirements. The 5G network is essential for developing a lightweight, adaptive, fast, and reliable XR service. And of course, it's crucial to choose the right IoT device. By taking into account all the above mentioned, we are able to design a powerful application combining all the state-of-the-art technology. So in this image, Qualcomm presents an XR service for emergency response in case of a fire of a building. The specific XR service relies on multiple data inputs. Firstly, thermal camera is used for temperature recognition. Additionally, multi-camera support with one front camera and one rear for better and more complete visual information of the environment. Real-time simulation, localization, and mapping for indoor navigation estimate the user's pose in a relative manner because it's not possible to have GPS on them. SLAM creates the 3D reconstruction of the environment, and the user can explore it through the 3D geographical information system for multi-user collaboration. Finally, machine learning or deep learning models can establish voice recognition and natural language processing in order to detect people in danger, and of course in multilingual environments. Now I would like to discuss the services and application in the IoT engine project that utilize extended reality and IoT technologies. Specifically, in IoT engine project, IoT devices and sensors are discovered using computer vision and deep learning methods through real-time video analysis in an XR environment. So the key stones to achieve this are, firstly, it is needed to create and maintain, of course, a repository of augmented reality and mixed reality software with libraries and tools to support augmented reality IoT interaction. Then design mixed reality interface standards between machines and humans employees. To improve real things object recognition, we will use visual and non-visual methods and AI techniques. So in the last section of this presentation, we would like to discuss some things about the XR open issues toward a tactile internet. Firstly, the XR glasses should be adapted to the upcoming telecommunication innovations. Secondly, XR framework must integrate state-of-the-art artificial intelligence and computer vision algorithms in an easy and user-friendly way. For a more immersive experience, more realistic graphics should be created. And of course, we should mention that power and thermal efficiency is essential for XR services and applications. So this was the presentation about designing IoT-powered XR services and application towards a tactile internet. If you would like, you can follow the IoT Engine project on social media and be updated all the time. And thank you very much for your attention.
Thank you very much, Stavroula, for this very nice tutorial. We have a couple of questions that we would like you to take. I don't know if you see the chat, but yeah, I'll read the first one from Mr. Theodosios Gamas. I don't know if Theodosios would like to ask the question, but you know, I just read it. Is if you have any knowledge or experience with Wikitude as you know, augmented reality platform with cross-platform option. So that's the first question. I don't know if you have ever used it or have any experience on Wikitude.
Personally, I haven't used the Wikitude. But it seems that, okay, I know some things about this tool. It's a promising augmented reality tool, but I think that Vuforia, due to the years of experience, it's more appealing. This is my understanding.
Yeah, I have a connected question to this because we've been doing a couple of projects recently. So I don't know what are the trends in the headsets and the AR devices in general in the costs, because we did an exercise for a railway company in the past and then for a manufacturer, and it was a really expensive project, for everybody to use. For example,
yes, of course.
which is something you want in the factory because it has this hands-free operation. It's much better than using the tablet or your smartphone. So I don't know if you have any idea about the trends, in the costs, and if these are going to become more affordable.
I think that throughout the years, the cost will be reduced. I hope so, and it will be more affordable to much more people. But of course, this is a new technology, and for this reason, in my opinion, it's in this price.
I think the prices I remember was a couple of thousands of euros.
Yes, too. I think for the HoloLens, the HoloLens cost 2,000, and some more.
It was even more expensive when we did the exercise. There is another question, Stavroula, by Jim Kurhi in the chat, which is why wouldn't the processing for extended reality be done on the edge instead? I think that was on one part of your presentation.
Actually, it depends from the processing and the processing capabilities of the edge device. I think that there are multiple solutions, and also it depends from the task that you would like to achieve. And a combination of this solution, I think it's something that can be done generally.
Maybe it's also a trade-off, right? Well, that's my answer. Trade-offs of what you want to achieve, right? Speed, latency, energy efficiency, or how many data points you may need for the application, and this impact whether you do the processing on the cloud or on the edge. Yes, Theodosius, please go on. I think we have the time, and then we can go to the Dresden presentation.
Okay. Thank you very much, Mr. Soulatos. I have a small question concerning the models of AI and machine learning and deep learning that I'm also using in my projects. Is it possible to make it run on a smartphone or on a tablet locally, not using any cloud services? I know that those kind of algorithms are very demanding in resources, in CPU and GPU resources and memory, of course. So do you think that there is a plan to go through that direction and have an algorithm, an efficient AI algorithm to be implemented and run locally on the device?
Of course, it depends from the task. Yes, generally for image processing, we need much more power, computer power. But generally, it's also many researchers that they are studying about how we can do like inference or even training in mobiles. Of course, there are also some platforms like TinyML, and also TensorFlow has a special version about the situation, TensorFlow Lite. So yeah, I think that's something that also it is studied from different researchers, and I think that at some point it will be easily achieved. I mean, also at some point until also now, it's achievable.
Theodosius, I would like to invite you to this is actually a good question, but for the previous training seminar we had, which was on edge computing and artificial intelligence. So, I mean, if you can check the NGIoT page, you can find the recording and you can find the presentations. and you will see what Stavroula was talking about. Yes, it is possible to build AI that does not need any GPU, but runs on an embedded device like a smartphone or even a microcontroller, right? So a tiny chip that you can put, in pervasively, inside the machine or any other physical context. And this works through TensorFlow Lite and TensorFlow Lite Mobile, TensorFlow Lite Micro and TensorFlow Lite Mobile. This approach is also called TinyML. There are several boards, Arduino, also from Infineon, from NXT, where you can, from ST Microelectronics, where you can test these developments. It turns out that it is possible to train a deep neural network using a normal, computing system, and then shrink the size, and you can run the deep neural network for image recognition even on a microcontroller. To put it very simple, it turns out that all these mathematical computations we do on matrices and so on, you can do on a microcontroller. Of course, you cannot process a large video, right? But you can process, for example, images, and this can be very effective. And I advise you, if you want, you can visit the Edge Impulse ecosystem, and there you will find a lot of tools that will get you set up and running on your smartphone in a couple of hours, okay, for something simple. It's called Edge Impulse, it's edgeimpulse.com. So yeah,
okay,
just
Mr. Soldatos, thank you for giving me all those advices. I just take them notes. So have another question concerning the demands of the stakeholders that always ask us to make a deep learning algorithm to be run on a web browser, for example. Is this also possible? Because I have some friends in the past that they were trying to run the deep learning algorithms on a web browser, and actually the laptop was burned out. Literally, it was the CPU was burned and never worked again.
Yeah, well, it all depends, as I told you, because I mean, what you run on the web browser, what we have is Jupyter Notebook, right? So I point you in the previous seminar. So yes, if you've got a lot of data and you try to train the algorithm on a simple PC, yes, you can run out of your device, right? You can exhaust your device. It is possible, right? So the approach is kind of different. You train the model in a more powerful setting, and then you deploy it. You shrink it, and you deploy the shrinked version on an embedded device. Okay, so
yes, actually, I'm familiar with this task. This is common to train the model in a cloud or in a powerful machine, and afterwards has the deployment or the testing on a small device, a smartphone or a web browser or whatever. Thank you so much, Mr. Soldatos.
So it depends, on the scale of the problem, right? So, we have built, recurrent neural networks or ANNs running on a microcontroller, right? Of course, this has some limits. Thank you very much, Stavroula, and thanks everybody for the questions.
Thank you very much.
I think we can move to the last presentation for today by TU Dresden and Ahmad Nimr, which is going to touch on the cross-layer aspects of XR and the tactile internet. So, Ahmad, the floor is yours.
Yep.
Let me know if you can share, the slides. Apologies, also we had some problems, by some mistake with your
Yes.
account. So I do apologize for this. And yes, the floor is yours.
So, yeah, now I'm trying to use my tablet, so I hope everything will be fine again.
Yes, we can see the slides.
Yeah.
To
Okay.
the first
Okay.
slide, feel free to introduce yourself and take your time. Thank you very much.
Yeah, thank you very much for this opportunity. So here with you, Ahmad Namr from TU at Dresden. So we are part of Ingenious project, and our main focus is on physical layer and MAC layer, and also like providing these special KPIs for tactile internet, and therefore that we also providing a view and a contribution about developing tactile applications. And when I say cross-layer framework here, so which means that it will not just focus on the devices, but also in the network, and how also all these components will be together. So this is, I hope this will be kind of like not more about the ideas, the concept. I hope it will be helpful. Yeah, so here's the table of content. So some ideas about the concept of tactile internet and how these tactile internet were defined, and which architectures are there, and then showing the tactile internet in relation to the operating system and applications. And we also, I would present our view in Ingenious projects and the work that we are gonna do in this regard. So first, so what is application? So application, if you look at the definitions of applications from Wikipedia, for instance, they say it's a computer program that is designed for a specific task, and this is targeting end user, and can be something to be distinguished from the system software, where the system software itself is the operating system. And then we have varieties of applications for desktop, for mobile, and also web applications. We talk about centralized applications running on one device, and nowadays most of the applications are distributed in form of web applications. And most of these applications then involve interaction between the user and input-output devices like keyboard, mouse, camera, microphone, and so on. And the operating system, actually, it's responsible for connecting these devices, scheduling them, coordinating the access and memory allocation, processing, and so on. So now if we define the tactile application, so it is an application running over the tactile internet. And what is the tactile internet? So the idea of tactile internet is to provide means of communications in order to provide the same experience dealing with the remote objects, which can be virtual or physical, and giving the same experience as you're dealing with directly connected device. So from this inspires also like to think about tactile application is a kind of, or tactile API or framework in general is a way that to provide seamless experience also for any programming developer, for any application developer to write applications as it is written on their computers. And for that, now what we need to define what is the operating system, which is related to the operating all the connected devices to the tactile internet, and the tactile and the requirement there, it's the same as the real-time requirement for operating systems. So we need to develop sort of real-time operating system, and this system should provide very high-level abstraction of the connected devices and the all the system-level management. Talking about application, so it can be seen from different perspectives, from control, from mathematics, from programming. So all these four diagrams here do the same job. So either we can give a command and process the command and give a response, and we have operator, or we have a program with input, then calling subroutine or a function, getting the output. So in control, we call them sensors, controller, actuators, and also in other applications can take request, server, answer. So what is involved here? Let's look at a simple example. If we have the mouse, a mouse is can be seen as a sensor or input device. We have the computer itself, the CPU, and the complete operating system will take these commands, translate these commands, and then send the response, the actuation, the answer, or any term can be used here, and showing that on a screen, so which is used as an output device, showing the cursor. So what I need here, I need the input, I need the computation, I need the output. So that means devices, computation, and the network between them. So then, thinking about a framework, we think first about the hardware architecture, devices, computation infrastructure, and communication infrastructure. Then the software or the system software here, the operating system, driver for the devices, and then all these network management stuff. So how then started, like, if we try to understand what is the tactile internet, it's good to start with the same simple example. In the past, like 10, 20 years ago, the mouse connected through a cable to the computer, and the monitors connected also through the cable. So we have nice experience with that, moving the mouse. We don't have any issues. We can see already the mouse moving on the screen. Then the next generation was using wireless technologies, like connecting using Bluetooth, Wi-Fi, or any other wireless technologies, just to connect these devices. That means breaking the cables using wireless signals. And then what if we wanna now reduce the amount of cabling and amount of links? And now most of the new devices, they have only one board, like USB-C port, and you can connect all other terminals to them using some hub here. So with the same mobile phone with USB-C, you can have a hub, connect monitor, connect mouse, keyboard, and so on. And so this can be done in wired way, but what if we want to do it in a wireless way? We can also use an access point. So if we have a Wi-Fi router at home, we can have all type of controls. Even nowadays, remote control can use the Wi-Fi to control your TV. So we don't need any sort of cabling. Everything is wireless, which makes the life easier, nice. But the further step is to go to do this remotely, that we have the computer is in a remote place, like nowadays the cloud computing. And then what I need input-output interface to, and all this stuff are far away. I don't need to listen to the noise of the fans from my computer. So everything can be in a remote server. But then what I need to guarantee for the user? It is the user experience. So the one who's using this remote communication in this way needs to be able to feel as these devices are directly connected. And that means we need some fast response. And how fast is the response? And this was the main driver behind the tactile internet. As an example here, if you we need to move the mouse with the speed or touch screen with the speed of 1 meter per second. And in order to not notice 1 millimeter displacement, so the latency between giving the command and getting the response back should be in order of 1 millisecond. So this is now the concept. That means, like, I need some communication to provide me with the fast response, such that I don't feel any strange experience or any cyber physics or cyber sickness. Now, from this example, we can understand more. So starting from different type of communications. So let's talk about the audio communication. Two persons talking together. So they have the human sensing, the hearing to hear the message, the brain to translate, and then they have the actuator, which is then we have the mouth to as actuator to talk, and then we have these bidirectional communication. Now, in order to do this in a remote or telecommunication way, what I need to do is to translate these human signals to signals that can be transmitted over a medium for long distance, and the same thing at the other side. So the main components of this human audio interface, it consists of sensors with a microphone, and the actuator is the loudspeaker, and then we have here also the encoding, so encoding of the signals and decoding of them. So this also, the principle is quite similar in most of the systems. And now what I need to guarantee for any phone call, that I need to feel like the person is next to me. So this is all about the experience. But what should be the latency technically that we don't miss the nice experience about conversation? It depends on the situation. So if we have only one talking, the other listening, on the other hand, like in sort of broadcast for entertainment, so it doesn't matter. If I listen to the song delayed 5 seconds, 10 seconds, it's not an issue. So I just need to guarantee that there will be no interruption between the buckets, which is the reliability needs to be sufficient, not to lose or to feel bad listening to some noise according to lost packets. But if we have also a question answer session, so one asks questions and the other waits, so the latency here is not very critical. But once we started a conversation and really like a strong conversation, and everyone started talking, and this is what noticed now when we having the telecalls, that whenever we try to discuss at the same time, so we have an issues understanding each other. But if we have the latency is in order of 100 milliseconds that is guaranteed in real time, so we should not have that issue. So this is an example, and then we have the other one, audio-visual communication, where now we don't only use one human sense, but we have more type of sensors. So we have here the microphone, the cameras, as audio and visual sensors. We have also the actuators, the speakers, the monitor, and the same. We need to do the encoding, decoding in a way that to have this signal propagate over channel, and we guarantee that we reduce the amount of exchange data depending on the bandwidth of the channel and so on. So this now to have also, what are the requirements to have a good conversation, audio or like visual conference and conversation. So it also depends on the context of the application. If it's a broadcast, it is fine to get the information a little bit late. We can wait for that, and that what could also the situation in nowadays webinars. The other case, if we have some live events and we have a broadcast, so the most important thing, for instance, if you were watching a match at home using the streaming or over the internet, and to guarantee that your neighbor is not this opening their TV, watching it from a cable TV, so there will be a latency of like 3-5 milliseconds, 3-5 seconds, and these 3-5 seconds will distract the enjoyment of showing the live scoring. And then the conversation is, then we go to latency of 20 milliseconds. So we still here in a type of communication that don't need 1 millisecond. But if we think now about the personal haptic communication, so haptic, something include the sensation of touches and also the pressure and so on. So these, the perception of these to be without any cyber sickness needs to be in order of 1 millisecond, especially for the response related to the velocity, the force, torque, position, and so on. But for tactile, for some to know about the shape, the texture, and hardness, so this still doesn't need that 1 millisecond, but need 10 milliseconds. So this is currently like, because the haptic communication is the main driver of tactile internet, so this is 1 millisecond. But of course, we might encounter some use cases that require less than 1 millisecond. But being able to achieve real-time latency with 1 millisecond and high reliability, that means the packet I sent arrive with high reliability to the destination within the time budget of 1 millisecond. So that will open the door for using the tactile internet in other domains. Now, so what are the other domains now? Instead of just talking about the haptic communication, the personal one, we talk now about controlling a machine, and this is one of the like most of the important use cases for remote or for tele operations. So, and yeah, this case, for instance, what we need to guarantee, for instance, like if I'm dealing with a steering of the car, and this has some haptic feedback to tell me like when turning, what will be the force, like to give me the same experience as driving the physical car. But here we're still talking about just the haptic, and here the requirements are just to guarantee that I have the response or the haptic feedback in real time, 1 millisecond. But still, the packet size is not so huge. It is really couple of bytes to convey this information. But now, if I wanna do something more elegant, like virtual and augmented reality, so now the requirements are different. So we have audio, we have video, and we have the haptic feedback, and we need to guarantee that all these three feedbacks that getting from the environment, they are all synchronized in a good way, so that to give me the realistic experience. And so then we have different requirements for communication, different data rates, different reliability requirements. So then I need to think about it as different links and what will be the requirement for each link in this communication use case. And then we have the issues of like providing what will be the distance between how far is the distance, and we are limited by the physics, so we cannot achieve 1 millisecond for more than 150 kilometers, for instance. But what we can do is to create the virtual environment, and in the virtual environment or in the physical environment, we have IoT sensors. So here is an interesting relation between IoT and the tactile. So the IoT sensors, which don't need high requirements for latency and reliability. So these sensors can be used to frequently update the virtual environment. And then instead of letting the haptic feedbacks travel through the remote network, we can make it travel through the virtual environment. So this is also another concept, like dealing with virtual objects, like dealing with physical objects. Yes, and so this is then the main concept of the tactile internet. So everything is about the realistic experience of dealing with remote objects, either physical objects or virtual objects. So this is the objective of the tactile internet. And then we can summarize here. So the so it involved the remote interaction, the real-time end-to-end response, and this response depends on the context, depends on the communication, the individual communication links. And then we have now many scenarios. So mainly the idea started by considering the human in loop, remote control with audio, visual, and haptic feedback. But okay, while we have now a low latency real-time network, so this can also be applied to industrial automation. And in industrial automation, the latency and the synchronization requirement for some applications that involve sensor control actuators. So these the latency here need to be first low, and also to be almost deterministic when we get the packets. So this is another important use case, and so we focus mostly in ingenious in one of the use cases, I mean, on the industrial automation. Yeah, now having the ideas, and now we start with the architecture. What kind of architecture? What is there? What we need to know in order to do the tactile internet? So what we need to know is that we have the tactile devices, and these tactile devices can be sensors, actuator, human system interface. So any device can fit here, and in order to and these devices need to be connected to the network. So either it has integrated connectivity, or it needs to be connected through some gateway. And we need a controller here for the network to assign the resources, to manage the network. And then we need some supporting engines. So these mainly are used for the computation, like edge cloud or any type of other processing that can be used. And then we need, so all these types now here, this type is called tactile edge, and sometimes like it's called here the master edge. And then I have at the other side the another tactile edge, and this tactile edge can be the slave one. And what I need is a network between them, and some service management. So this service management can be exposed to the external world. The most important now, so this standard talks about devices. They need this and that. The network should be able to do this and that, but they didn't specify exactly what should be the network. Is it 5G? Is it Wi-Fi? So the network is anything, can be anything from wired to wireless, standard, non-standard, and so on. And the devices can do also anything, but they need to be able to connect the network. So for that, we have the interfaces for communication between the tactile devices. And for accessing to the network, we have interfaces with the supporting engine for the computation, and also with the service management. Yeah, so here just some examples about the devices. So any device can be for like sensors, different types of sensors, from computer devices, cameras. Even here we have radar input. So this the radar can the one that can respond to the gesture. Any type of audio video output could be a standalone or integrated tactile device that have the input and the feedback in one device, like tactile gloves. Also the robots, AGVs, and we could also think about the virtual and augmented reality interface. That's the complete interface. One just need to go inside and live the experience of the virtual world. Yeah, so this the first architecture, considering this gateway and network as related more to the tactile edge, but the other architecture, which is, I think, more appropriate for the development, is integrating the gateway and network controller within the network. And this is the case, for instance, for 5G, where we have the G-Node B with some mobile edge computing, and then all this stuff can be realized here. So, and now the concrete example about this, we in NGIoT, we consider now that we are in a factory, and in a factory we have different types of devices, and these devices can have any type of connectivity or without connectivity, such that we can add connectivity to them. And to cover the area of the factory, so we could have several access points from different radio technologies. Yeah. So we have two, like the partners in NGIoT, some of them just focus on the tactile devices, some focus on the network and the network developments that we need to do here, something related to IoT gateway, the flexible radio access network, and also some time-sensitive networking. And some other partners focus on the interface to the mobile edge cloud. Yeah, so now having this infrastructure in mind, now what we need to do in order to say, okay, look, we have now the infrastructure for Tactile Internet, we need to define the interfaces. Yeah, and then in order to start our idea, providing the vision that the tactile application development should be similar to development on a computer system, so we propose to model again the network or the architecture of the Tactile Internet in a form of computer architecture. So what we have here, that the computing or the MEC in the network, they act as the computer CPUs, and then we have the devices for input output. The network provides the system bus that connecting everything, and what is remaining is to have the management and orchestration, which plays the role of the operating system of the network. And once we have this architecture defined the interfaces, so we could follow the standard using the access interfaces between the device and the network, and the other interfaces mentioned in the architecture. We can say that our architecture is ready, and now we should focus on developing the applications. So how to develop an application for the tactile application? So the first thing, we need to determine the end-to-end requirements. So first, determine the application needs how many links, what type of communications there, what are the requirement for each links. And this requires some also work from psychology to provide the perception models, to understand the context, and then to determine these requirements. So now we can see a lot of papers just listing tables for the requirements for different applications. And then, so this part can be done offline. The online part is now how to do the initialization based on the network resources. So to do so, we can see that different control loops in the tactile application. I mean, this is just input, output, and functions, but this is like a common model. So what is the type of latency I need, or what is the latency required? What is the reliability? And then I have this whole link or latency budget need to be distributed on different units. So the crucial units are the processing. So if we have some encoder for like codecs for haptic, audio-visual haptic codecs, so might need amount of processing, which could be the main source of latency. We might need very high bandwidth also for some to provide high definition videos. So all this needs to be analyzed and find out what is the processing requirement for my application. So is this processing available in the infrastructure, and what are the radio resources required for specific control loop. So once getting that, needs to have also implementation for some software units. Like if you have some control algorithms need to be implemented. If I have some GUIs, so everything need to be deployed. And one other aspect also we consider in Genius is like using flexible or configurable FiMac that could be beyond the 5G Neo radio. So this could be also about what kind of configurations I need to configure the links. So once this initialization phase is done, we can start the application, and where the devices start exchanging the information with the processing units and so on. And then the operating system needs to make sure that the links requirements are maintained, any errors happens to react to that. So it is really complicated, like very demanding distributed computer system. And once the application is done, we need, as we do normally in computer program, just release the resources. Yes, so one of the main focus, so as I said, it is for TU Dresden, it's on the Pi and Mac, and here we are considering the work related to develop deterministic Mac, which is some important aspect to for real-time communication. Also at the physical layer, different algorithms, optimization for the complexity, and also the radio resource requirement. In addition to using software-defined radio, multi-connectivity, and so on. So this the FiMac it's really essential also for the tactile internet. Yeah, and here's an example. Just how to map this to the architecture. Let's talk about the teleoperation. So I have this architecture now in a computer. What are the devices? So this is in the initialization phase. We decide which devices we need, and then set up the network for them. So what are the loops involved here? We have different loops with different requirements. We have the human interface with haptic sensors, need to translate the human sensors input to the haptic codecs that might be running on the MEC, and then the MEC will translate these sensor commands to command corresponding to the AGV. The other one is reading the haptic sensors from the AGV, like the position and other sensors related to the haptic feedback, and then provide them back. Also, we have the cameras, where these cameras also need to feedback the visual area. So we see here like the main three loops, so with different requirements in terms of latency, the packet rate, the packet size, and also the reliability. So the network, then the initialization phase, need to be sure that the network can fulfill that before running the application. So now a slight modification of this application can be translated to autonomous driving. And in autonomous driving, what we need is no human interface, but maybe we need a graphical user interface just to observe what's happening in the automatic application. So here, less number of loops, different requirements, depending on the scenario. For instance, let's take a simple software or end user application. So this application says that I wanna the AGV to move in a certain path, and this AGV should stop if it encounters an obstacle or reach the end of the path. And then I would allow the user to change the path. It is not necessary in real time. So we're not talking about following the finger, for instance. No, just changing the path. So what we need here to define the requirements for the for the communication requirement between the devices, and also need to support the GUI. So this example scenario. So this assemble user interface. So the user interface. So this is kind of application provided to the end user, and the end user need to click run, pause, finish. So run means like do the communication. Pause, stop the communication, but keep the resource allocated. Finish now correspond to releasing the resource. So once this application starts at the first time, so it needs to do the initialization by reservation of the devices and checking the requirement. Then it comes to the running phase. So this what could be an end user programmer, right? Move AGVE forward, stop if there is an encounter, and always read status. And this will be in a while loop. And this status will go now to update the GUI. So below this one, so this is the top level, but we have a lot of works in order to fulfill that. We need to have some function libraries provide functions about the control. For instance, I can have an algorithm about the object detection that need to be run on the Mac. So this kind of functionality, third party can provide it, or we can borrow it from already existing applications. And then we have the underlying is the communication between the devices. So some of these commands and translated to which packets need to be sent and how to respond to that packets. And this will be the very low level reading the devices, and this corresponding sort of to the driver of the devices. So we have different level of application development involved, from the end user to some libraries for the control algorithms, and the most complicated work is at the lowest level, which is really which is near the hardware. Yes, and finally, so in order to prove this or to demonstrate all these concepts and to work on it, so we first created a test bed, indoor test bed for emulating an industrial scenario with different type of devices. So devices that require with the tactile internet requirement, other devices, IoT sensors with simple requirements. And then we have different access points and gateways to cover the area, and then a centralized unit for the core network. And we rely on software-defined networking, where we use some USB devices with SDR and FPGA capabilities. And we can use a host computer to emulate devices. And yeah, depending on the type of device, we can select the type of the USRP. Yeah, and then so this will be our model for the development, like the computer system model. So first, we need to design or to focus, or different partners would focus on designing different APIs for the devices, for the interaction with the devices and the control algorithms, and also some end-user development, something like user interfaces or web applications. So the first step, like we can remove the network in order to validate the interaction between the devices, and that also will give a chance to measure the latency corresponding to the processing. And once that is done, we can evaluate using a fixed network and see what kind of problems arises. And after that, the wireless connectivity with manual resource allocation. That means now the operating system is idle or not used. And then finally, one of the partners in the project is working on the management and orchestration concept mainly for 5G networks, but we're going to adapt this to any type of network. And once everything is done, hopefully, then we can have a final demonstration. So this is our goal now in Genius, is to proof concept this, and hopefully we'll be able to show many type of end user applications. Yeah, so yeah, in conclusion, so that was about the tactile internet. So in summary, it is a network with real-time capabilities. And this real-time depends on the context of the application and also the perception of the human and machine. And then we can think about it as a distributed computer system with many devices, different requirements, and a with high performance network. So then the tactile application development, instead of starting from the scratch, we can go through what is the already mature technologies in computer programming and try to bring that to the tactile internet instead of just thinking about applications independently. Yeah, and finally, this kind of cross-layer framework. So this is involving the network as well as processing in a joint optimization way. To this is important in order to, for instance, to focus on reducing the energy consumption of the overall system. So that was from my side, and I think I took longer time than expected, but I was in the beginning told that I could be relaxed. Thank you, John.
That was really an excellent presentation, especially of the systemic aspects, right? That were not, so much detail in some of the previous presentations. So thank you very much, Ahmad. I think that was a rich presentation. We have just one question in the chat that I would like to answer, and then I will wrap up and close the session. Sorry for taking too long. So the question is by Jim Udehib again. From a security perspective, is there use cases where confirmation process needs to provide an additional and isolated monitoring that confirms the actions of the sensor or actuator?
Okay, so the question in the chat, okay?
Yes.
Yes, actually, the security, it's very important part, and we don't I don't consider in this presentation because it's not my my expertise, but we are working with other partners such as to provide security at the hardware level, and they will make sure about the security. And once we implement like the processing and other stuff, so this will be implemented on a secure by design software. So this is at one side, and at the authentication side for the network also. Yeah, we might, as I say, it's not our expertise here, but we can rely on the approaches now provided by 5G for authentication and registration of the devices. So so the devices will not be directly connected to the network. So there will be the normal initial access process where these devices need to be authenticated and so on in order to be part of the network. Yeah, I hope I could answer the question or not. If you have more, we can discuss.
So can I just quickly add a little bit there?
Yes.
So it was more about if, let's say, it gets compromised, and think of there's been incidences recently where I'll give a good example, like a water treatment plant, where someone got the environment was compromised, and let's say chlorine should be 20 parts per million, and they were able to make it 10x, 100x that, which becomes a dangerous level. And instead of the sort of, since that environment's already been compromised, the sort of the sensor actuator, is there a thought that there's be like another completely isolated process that would monitor these things and realize something's drastically wrong, and there's a potential where the compromise would be sort of indicated at that point? That was really what I was getting at. And I know it's not like an everyday use case, but I can see other examples. And I understand what you're saying about the security. There's control planes you talk through, whether that's through your pub sub models. I get all that, but I was really asking, as part of the architecture, do people think about these things, that maybe there needs to be like something very isolated and separate that actually sort of monitors this? And that's really what I was asking.
Yeah. So to my use, the first use case that I'm targeting is the something like private network and industry. So it should, like, even the designing for the communication could be like the operator itself can know exactly what is going on. But the issue you raised, it's yeah, definitely important, but unfortunately I don't have any convincing answer. But yes, this is need at least to be considered, these issues, even in at the let's say at the overall network operating system, and also it will be sort of the KPIs that need to be provided during the application or the design and the stage of the application design. And these KPIs also need related to the security need to be highly considered. Yes.
Okay, since we are also over time, I would like to thank very much all the speakers and also the participants. We had a very active discussion this time. I would also like to repeat that recordings and presentations will be made available to all registered participants. And I also would like you to stay tuned for the next training seminars we're going to have in the next series, dealing with other important topics like 5G, architectures for Internet of Things. This is one of the upcoming seminars, next generation edge architectures for Internet of Things. And of course, we will have some thematic seminars on different types of application sectors. So for all of this, stay tuned with EU-IoT project, NGIoT, the web page, the channels. And thanks again once everybody for contributing and for participating to this seminar, especially to our speakers for providing such a great content. And I'm really, not exaggerating. I think I echo everybody's opinion on this. Thank you very much, and see you soon in one of the next seminars.
Thank you.
Bye.
Thank you. Bye-bye.
Thank you very much. Bye.
Thank you. Bye.
Thanks. Bye.